Mhm. Oh, hi. Okay, congrats on passing the AP Chem. So today I will briefly go over the Unit 1. Okay, and then I will go over the progress check of Unit 1. So Unit 1 is about atomic structure and properties. So there are a lot of basic concepts such as moles, the molar mass, and then the mass, and the mass spectroscopy, and the isotopes. And then it's going to be the pure substance versus mixture, the way we classify the matter in the world. And then it's going to be the history of atomic structure, how the atomic structure has changed over the past 200 years, and then how we eventually come to the Bohr model and then the electron cloud atomic structure these days. And then next is electron configuration. So after we studied the atomic structure, we're going to study how electrons are, the electron structure. So how electrons are moving around the atoms and how they are arranged in the sublevels and orbitals. And next, that's going to be the photoelectron spectroscopy. Again, anything that ends with like COP means it's a type of chemical method to test some kind of material or test for the property or to identify the chemical property of a substance. And next is periodic trends. So there are four chemical quantities that you need to memorize when it comes to periodic trends, including the atomic radius or the atomic size, and the ionization energy, and the electronegativity, and then electron affinity. There are four in total. And the last but not least is the valence electron. So after we learn the valence electron, then we can talk about the ions and then the ionic bonds in Unit 2. So that's it for Unit 1. Um, so I will start with a very basic definitions of the moles and the molar mass. So we know that chemistry is a quantitative science. It's not just a chemistry. It's also the physics and bio and then a lot of other science. So qualitative versus quantitative. Quantitative means it's measured in a very specific number. So you need to actually measure something and then you need to put a unit to specify the amount. So let's say 30 grams or 2 meters, like 1.5 liters. All of these are quantities of very specific numbers, numerical value. So qualitative means you're describing something. So let's say, oh, chemistry is very difficult. So very difficult is qualitative, or very easy, that's qualitative. On the other hand, quantitative gives you a very specific number. Let's say, like my class has an average of, let's say, 88 in chemistry for the quiz. My physics class has an average of 91 with a standard deviation of 10. Then these are what we mean by the quantitative. So because chemistry is a quantitative science, so we actually need to measure the amount of the materials or the amount of the matter, the amount of the reactants and the products in chemistry or chemical experiments. The thing is, we cannot count the particles directly. Well, I can count the number of a lot of objects, such as like one iPhone, two iPhone, three iPhone, one MacBook, two MacBook, three MacBook. We can actually count them because they're tangible, and then it's pretty easy to count them. But when it comes to tiny particles such as the atoms, such as the electrons, such as the protons, or molecules, or the ions, we cannot count the number of the particles directly because they're so tiny. So every single particle, like these little particles, are not even tangible. When you can touch a matter, then it means it must be a whole chunk of the particles, not just one simple particle. They're way too tiny for us. So this is just like you cannot count the amount of the sand at the beach. There are just way too many. So what we can do is, instead of counting the actual number of those particles, we can measure the matter by the mass by using a scale, or measure the volume by using a beaker beaker when it comes to measuring the liquid, or by measuring the volume of a container when it comes to the gas, or by calculating the volume it's occupied when it comes to a solid, or we can measure it, or we can measure the amount in terms of the mole. So mole represents the number, or it represents the number of the packets of a matter. So just like a dozen, mole is just a unit for measure. So one dozen of donuts means 12 donuts, or one dozen of eggs means 12 eggs. So one dozen is just a packet of 12. That's the way for us to measure something for convenience, because you don't want to count the number of the eggs every time you go for grocery shopping. So that's similar in chemistry. In chemistry, okay, so in chemistry, we're going to use mole to measure the number of the particles. And then 1 mole is equal to 6.022 times 10 to the 23 particles. And here, when I say particles, it can be either molecules, it can be molecules, or the ions, or the atoms. So all of these are considered the particles, like the tiny particles in chemistry. And then we call this number the Avogadro's number. This is what we call by the Avogadro's number, and then we use the capital letter A N to represent the number of the particles. So A stands for the Avogadro. So Na is equal to 6.022 times 10 to the 23. Okay, so again, this is similar to a dozen. A dozen is equal to 12. A mole is equal to 6.022 times 10 to the 23. And how we got this number is by approximating or measuring the number of the carbon atoms in 12 grams of the pure carbon, in the pure carbon 12. So to be honest, for every single atom, they have actually a slightly different number of the particles in 1 mole, but we just use the carbon 12 as the standard, as our reference. So that's what it means by the Avogadro's number. So let's say here we have a really simple chemical equation. How we read it is not 2 hydrogen particles react with 1 oxygen particles. No, we don't use the particles when it comes to chemical equation. When it comes to chemical equation, and when you read it, you always read it in the unit of a mole. So it means 2 moles of the hydrogen in gas reacts with 1 mole of the oxygen in gas to produce or to form or to yield 2 moles of the water in liquid. That's how we read a chemical equation. So when it comes to chemical equation, all of these coefficients, the coefficients means the number of each of the reactants and the products. So the coefficients in this chemical equation are 2, 1, 2. So these coefficients refer to the mole. We assume that it has the unit of the mole, not the particles, not the number of the particles. It must be 2 moles react to 1 mole of oxygen to produce 2 moles of the water. Okay, so that's the definition of the mole. Okay, once we know the definition of the mole, I can talk about the molar mass. Well, we know what it means by the mass. Mass is a quantity. It's a quantity that we use in science to measure how heavy an object is, how heavy a sample is. And molar mass means the mass of a sample or the mass of a substance for 1 mole. Okay, so let's say the price per dozen, the price for X. We barely calculate the price for 1 single egg because usually we buy the eggs in the unit of a dozen. So we prefer to talk about the price of the egg in terms of 1 dozen, right? So that's similar. Molar mass means the mass of a substance for 1 mole, for a 1 mole amount. Okay, and then how we calculate the molar mass, or how we know the molar mass, is just by checking the periodic table. So on the periodic table for each of the cube, each of the box represents each of the elements, and then the number at the top of the box represents atomic number, which is also the number of the protons. So this is like the ID card of a. This is just like the ID card of each of the elements. And then at the bottom, we have number such as 10.1 and 10.81 for the boron. And it represents the atomic mass for the element boron, or 12.01 for the carbon. That represents the atomic mass for the carbon. Okay, then for each of the elements, these number at the bottom represent its molar mass. Well, for the molar mass, we have the unit of the grams per mole. So let's say for the carbon, its molar mass is 12.01 grams per mole. And for boron, its molar mass is 10.81 grams per mole. And then for nitrogen, its molar mass is 14.01 grams per mole. That's how we calculate the molar mass of each of an element. Okay, then what about the molar mass of the molecules? Or for the ionic compounds. Well, so let's say CH4, this is a molecule. Then how we calculate the molar mass of the methane, CH4, is by adding up the molar mass of the 1 carbon and the molar mass of the 4 of the hydrogen. So now we have 12.01, that's the molar mass for 1 carbon, and then plus 4 times 1.008, that's the molar mass for 4 of the hydrogen. And then add them up together, then you will get 16.04, or approximately 16. So you always need to put the mass when it comes to molar mass, or when it comes to any of the physical quantities. So it's going to be 16 grams per mole. That is the molar mass of the methane. Okay, and then when it comes to the mole, we use the symbol N to represent it. When it comes to molar mass, we use the capital letter M to represent it. When it comes to just the mass of a sample, we use the small m to represent it. Okay, then how do we do the conversion between the moles, the molar mass, and mass? This is really, really, really important. So we always use the formula M is equal to N times M, which means the mass of a sample is equal to the moles, its moles multiplied by its molar mass. So let's say now I have 0.6 moles of the methane. Then what is the mass of this amount of the methane? Then it's going to be 0.6 mole multiplied by 16 grams per mole. And then you will get 9.6 grams. So that's the mass for 0.6 moles of the methane. Okay, then how do we calculate the number of the moles when you're given the mass and the molar mass? That's going to be number of the moles, N is equal to mass divided by the molar mass. Or when you're given the mass and the number of the moles, how we calculate the molar mass is M, capital letter M, molar mass is equal to mass divided by moles. Well, so anyway, you do not have to memorize everything. You just need to memorize this one single equation. And then from this one, you can just derive whatever the equation you want. So do not try to memorize everything. Just try to memorize this one. That's the most important one. That's it. Okay. And next, okay, so here we have a pretty easy example questions to do the conversion between the moles and then the molar mass and then the mass. The jagulan is a dye known for centuries, and it's produced from the husks of black walnuts, so a type of tree. It's also a natural herbicide that kills off competitive plants around the black walnut tree, but does not affect grass and other non-competitive plants. The formula for jagulan is C10H6O3. A. Calculate the molar mass of the jagulan. So again, how we calculate the molar mass of a molecule is by adding up the molar mass of each of the components. So the molar mass of C10, the molar mass of C10H6O3 is going to be 6 times the molar mass of the carbon plus, in fact, not 6, 10 times the molar mass of the carbon plus 6 times the molar mass of the hydrogen plus 3 times the molar mass of the oxygen. So that's 10 times 12.01 grams per mole plus 6 times 1.01 grams per mole plus 3 times oxygen. I think that's 16 16 grams per mole. And then use calculator to calculate it. That's it. Okay, and in the end, when you eventually got the answer, you need to always put the unit, which is grams per mole. Okay, and what about B? A sample of 1.56 times 10 to the negative 2 grams of pure juglone was extracted from the black walnut husk. How many moles of juglone does this sample represent? Well, give me 1 second. Let me try to calculate it first. So we have 55.26 grams per mole. And for B, okay, you're given the mass because the unit is in grams. So I know for sure the mass is given. And then it's asking for the number of the moles. So now what we want to do is I want to go from mass and the molar mass to the number of the moles. Again, we're going to use the formula. We're going to use the formula of mass is equal to moles multiplied by the molar mass. And now I want to calculate the N. Then N is equal to mass divided by molar mass. So that's equal to 1.56 times 10 to the negative 2 grams and divided by the molar mass that we just calculated in part A, which is 55.26 grams per mole. Okay, so now you notice that we have grams in numerator and in grams in denominator. So the grams are canceled out. Then we're left with the unit of the mole. And again, just use a calculator to do the calculation. That's it. Okay, and next, another sample questions. Calcium carbonate CaCO3 are called calcite, and it's the principal mineral found in limestone, marble, chalk, pearls, and the shells of marine animals such as clams. A. Calculate the molar mass of calcium carbonate. Again, pretty similar. It's similar to the last question we did. So the molar mass of the CaCO3 is equal to molar mass of calcium plus the molar mass of carbon plus 3 times the molar mass of the oxygen. And it's equal to calcium, it should be 40. It's 40.08 grams per mole plus 12.01 grams per mole plus 3 times 16 grams per mole. And then I get 100.09 grams per mole as the answer. And this is the molar mass of the calcium carbonate. B, a certain sample of calcium carbonate contains 4.86 moles. What is the mass in grams of this sample? What is the mass of the carbonate ions present? Okay, so there are 2 questions in part B. Okay, so we're given the number of the moles this time, and it's asking for the mass. Again, we're going to use the formula. Of mass is equal to moles times molar mass. So mass is equal to number of the moles, which is 4.86 moles, multiplied by the molar mass. The answer we just got in part A, which is the 100.09 grams per mole. Then we get 486.44 grams. Okay, so this is the mass of the mass of the sample. the sample of the calcium carbonate. And the next question is, what is the mass of the carbonate ions present? Okay, so we're going to use the ratio. So this is actually the mathematical part. So think of every single calcium carbonate molecule. For each of the calcium carbonate molecule, it consists of one calcium and then one carbonate ion, right? That's equal to one calcium plus one carbonate ion. So it means that for every one calcium carbonate molecule, there is one carbonate ion. So first off, we just need to calculate the number of the moles for the carbonate ion. And then by that we can calculate the mass of the carbonate. And then remember that the ratio is 1 to 1. And it's really given that the number of the moles of the calcium carbonate is equal to 4.86 moles. Then it's pretty easy to calculate the number of the moles of carbonate ion. Here again, we're going to use the conversion factor of 4.86 mole of the calcium carbonate. I'm going to multiply by the conversion factor of 1 mole over 1 mole. But what is that exactly? That's going to be 1 mole of the carbonate ion over 1 mole of the calcium carbonate. By then, mole calcium carbonate and mole calcium carbonate are canceled out. So we're left with the unit of the mole carbonate ions. So we have 4.86 moles of the carbonate ions. And then we're going to start from here to calculate the mass of the carbonate. The mass of the carbonate is equal to number of the moles times the molar mass of the carbonate. So that's 4.86 mole multiplied by the carbonate. Okay, the molar mass of the carbonate is going to be molar mass of the carbon, 1 carbon, which is 12, plus the molar mass of the 3 oxygen. That's going to be 3 times 16. And again, use a calculator. We will get the answer of that's approximately 201.6 grams. That's the mass of the carbonate in this sample. Okay, so that's it. That's it for the moles and then the molar mass. And there are more questions, but I want to just get into mass spectroscopy because I want to go over all the Unit 1 concepts today. So mass spectroscopy is a chemical method to identify the isotopes, to identify different isotopes of one single element. So anything that ends with scopy is going to be a type of a machine. It's either a machine and apparatus or a type of method to measure something or identify something or differentiate something in a matter. Okay, and first off, we need to talk about what it means by the isotope. So we know that what it means by an element is, okay, on the periodic table, we do see all of these elements. So each of the cube, each of the box represent different elements. This is boron element, this is carbon element, this is nitrogen elements. And what I mean by the element is they are the atoms, they are the tiny particles that have the same mass and identical mass and identical properties, which means all of the boron atoms, all of them have the same size, same mass, and the same property. All of the fluorine atoms, all of them, no matter where you find these fluorine atoms, you can find in UK, in US, in Australia, in Korea, and then all of these fluorine atoms, they share the same chemical property, they share the same mass, and then they share the same size, etc. So that's what we call by an element. And then we know that atoms are the smallest building block of the matter in the world. Then what are the isotopes? For some of the elements, they have different mass. I mean, we claim that all of the atoms of one single element should have the same size and same mass. But for some of the elements, they're a little bit different. It's just like twins, identical twins. We know that identical twins are born with exactly the same DNA. So when you run the DNA test and then the fingerprint test, identical twins have exactly the same DNA and then the same fingerprint. But let's say they're raised in 2 different ways. So one of them is a little bit chubby, the other one is a little bit skinny. So even though they have the same genes, their look might be a little bit different, and then their weights are also different. So isotopes are just like the identical twins, and one is a little bit bigger, the other one is a little bit smaller. So isotopes of an element have the same number of the protons, but different numbers of neutrons. And then we know that how we calculate the atomic mass of an atom is atomic mass average, atomic mass is equal to number of the protons plus number of the neutrons. Well, so it's supposed to be a whole number. So proton and neutron, proton carries the positive charge, and then neutrons, it does not carry any of the charge, it's neutral. And then they have approximately the same size and approximately the same weight. Their weight is not exactly the same. The ratio is 1 to 1.01. So one of them is a little bit heavier than the other one, but approximately they have the same weight. So that's why when we calculate the atomic mass, we just add up their numbers. But on the periodic table, you will observe that some of the elements have very weird numbers, a number that's not close to a whole number at all. Okay, so let's say, let's say chlorine. So chlorine has an atomic mass of 35.45. So 0.45 means that it's nowhere close to 35 or 36. It's not close to 35. It's right in between 35 and 36. So why? Because when we count a number of the protons or the neutrons, it's supposed to be a whole number. So when you add them up, it's supposed to be a whole number as well. But for some reason, we have this weird decimal point. And that's because of the isotopes. So that's because chlorine has more than one isotope. So chlorine has two isotopes. One is chlorine 35, and the other one is chlorine 37. And what I mean by 35 and 37 is the atomic mass. Well, based on the periodic table, we know that chlorine has an atomic number of 17, or the proton number of the 17, which means for chlorine 35, it has 17 of the protons, and then it has 35 minus 17, which is 18 neutrons. For chlorine 37, it also has 17 protons, but it has 2 more neutrons, which is 20. Okay, so that's why these two chlorine isotopes have different atomic mass. Okay, and then what happens is based on their abundance, based on their percentage that represent in nature, we're going to calculate the weighted average. Okay, what is weighted average? So when you calculate the average of two numbers, let's say 35 and 37, what we do is usually just add them up and then divide it by 2, so we get 36. But sometimes they're weighted in different percentage. So let's say when you apply for college, you're gonna submit your average, your GPA, and then a lot of times it's going to be the weighted GPA. So let's say your GPA in the junior years weighs a little bit more than your GPA in your freshman year. So that's what we mean by the weighted average when it comes to average atomic mass. So for chlorine, for example, 75% of the chlorine in nature is chlorine 35, and only 25% of the chlorine in nature is chlorine 37. So the ratio is not 1 to 1. We have 3 times more chlorine than chlorine 37 than chlorine 35. So how we calculate the weighted average is 75% times 35 plus 25% times 37. Then we will get 35.5. So that's approximately 35.45. So it explains why chlorine has such a weird a non-whole number atomic mass, because this is the average atomic mass. We call it average atomic mass, AAM. And average atomic mass is actually the weighted mass of all of the isotopes of an element. Well, the thing is, how do we know there are different isotopes for an element? Because the particles are so small, the atoms are so small, and then we cannot even observe it with raw eyes. And of course, the scientists are really smart, so they come up with a machine called mass spectrometer. So this is mass spectrometer, and then they're gonna put the samples for the chlorine. Let's say for chlorine, they're gonna put a tiny amount of sample in this machine, and then this machine will convert the sample into gas. into the gas phase, and then it's just gonna spray the gas particles into the machine. And then in the very first phase they go over, the experience is the electron. There are some a sample heater, so it's gonna vaporize the sample, vaporize the chlorine atoms, and then on the other side there is an electron beam. So electron beam carries a pretty strong energy. It carries a lot of energy. So what happens is electron beam is gonna knock off. It's gonna knock one electron away from this chlorine sample. So now the chlorine atoms have been converted into chlorine plus after one electron has been removed. Okay, so these atoms, chlorine atoms, pass through the accelerator. So the accelerator is gonna make these chlorine atoms to go faster and faster. So they're gonna have a really fast speed, and they're gonna move along the straight line. Okay, and then here at the corner there are two huge magnets. So when the charged particles are passing through the magnetic field, they're not going to go in a straight line. They're going to bend. They're going to go around a corner. And then it really depends on how much they go around a corner or how much they deviate from this linear line path. Depends on one, their charge, and two, their mass. Well, we know that both of the isotopes carry the same charge of positive 1. So now it really depends on their mass only. So for these two isotopes, one is chlorine 35 and one is chlorine 37. So chlorine 35 is a little bit skinnier or a little bit lighter. So the lighter one is going to bend a little bit more. So think of two athletes. One is fitter, the other one is a bit chubbier. Then usually the more fit athletes are more agile, and then they can move faster, or they can when they go around a corner they can bend more. So this is where two isotopes deviate from each other. The skinnier one, the chlorine 35, chlorine plus 35 will bend a little bit more, and then chlorine 37 is not going to bend as much. So this is where these two different isotopes of the chlorine land on the detector. And then the detector will is connected to the software in a computer. So it's gonna print out all of the information, and then it's gonna tell you how many isotopes there are in this sample, and then the relative abundance or the percentage of each of the isotope in this sample. So that's it. This is how a mass spectroscopy works. And then this is how, this is how a mass spectrometer works. A mass spectrometer, that's the machine. And then now mass spectroscopy is something that's printed in the software in your computer. So it's a graph. It's a graph that tells you or shows you all of the isotopes in this sample and their relative abundance. So what I mean by the relative abundance is the percentage of these isotopes in the whole sample. So let's say for chlorine, I told you that there is 75% of the chlorine 35 and only 25% of the chlorine 37. So that explains why these two peaks have the height ratio of 3:1, because 75% to 25% is 3:1. Well, but a lot of times you're not going to be given the percentage. A lot of times you're only given their height ratio, such as 3:1. Then how we calculate the 75% and 25% is by calculating these numbers. So 3 plus 1 represents the total amount of these isotopes in a sample. And then the 35, the isotopes with a mass of 35 occupies 3 out of 4. So that is 3/4, or it can be simplified to 0.75, which is equal to 75%. On the other hand, the isotope with an atomic mass of 37 occupies 1 out of 4 in this sample, which is 0.25 or 25%. Okay, a lot of times in AP chemistry, you're not asked to actually calculate the average atomic mass. A lot of times you're required to calculate or estimate the average atomic mass in MCQ question. So such as this one. So this is, I believe this is for zinc. And then there are a lot of isotopes, multiple isotopes. And then how you actually estimate the atomic mass is by by calculating the weighted average, right? So I know for sure that the atomic the element with atomic mass of 90 occupies 50% of the sample, and then next 92 and 94 they occupy approximately 15%, like 17%, right? And then it's 91, it's a little bit more than 10%, probably 12%, and then the 96, it occupies it very little, such as 3% and 5%. So it's actually impossible for us to do all of the calculation. So I can only estimate it. So first up, what I'm going to do is I'm going to pay attention to these two, 92 and 94, because these two have approximately the same height, which means they're in the same ratio or the same amount. So when I calculate the average of these two, it must be 93. Okay, so I can get rid of these two bars and then I can draw a new pick or a new bar at 93. But now its height must be twice as high. Its height must be the height of the 92 plus height of the 94. So now these two are gone, but instead I have a taller peak. I have a taller peak here at 93. Okay, so now I just need to calculate the average of 91 and 93 and 96. Well, 96 is it's very short. The peak is very short. So let me just omit it for now. Okay, then what about the average between 91 and 93? Well, their height difference is their height is approximately at the ratio of 1 to 3 or 1 to 4. So approximately, when you calculate the average of these two, it should be somewhere around here, around 92.5. So get rid of these two, and now I have a taller pick right here. And then the height of the pick should be the height of the 91 plus height of the 93. Okay, and then I also need to consider this very little amount 96. So it's this pick is going to shift to the right a little bit. Shift to the right. Oops. Shift to the right a little bit because of 96. Okay, and then it should be approximately 50% now. And then the isotope with a mass of 90 is also approximately 50%. Now I just need to calculate the weighted average of these two picks. And because they're both 50% and 50%, I just need to calculate their average. That's it. So 90, and this is approximately 92 point, I don't know, 7. Okay. Then when you calculate the average, it should be approximately 91.4, 91.3. Yeah, it should be approximately here. So that's how I do the estimation. So in MCQ questions, you wouldn't be asked to do the actual calculation. Usually how they ask you the question is, out of all of the followings, which one is closest to the average atomic mass? And it's going to give you a bunch of options, such as 89, such as 90, such as 91.3, such as 92.6, 94.5, something like that. So I know for sure that it must be something in between 91 and 92. So that's how you choose the answer. Okay, and next, this is an FRQ question for the isotopes and mass spectroscopy. The average atomic mass of naturally occurring neon is 20.18 AMU. AMU stands for atomic mass unit. So that's this is the unit for each of the particle or each of the atom or the ion. And then for any atom or any molecule or the ions, they have exactly the same numerical value when it comes to AMU and when it comes to grams per mole. So the numerical value of the molar mass is always equal to the numerical value of the mass of each of the atom. So it literally means that neon 22 has a molar mass of 19.99 grams per mole, and then neon 22 has the molar mass of 21.99 grams per mole. There are 2 common isotopes, blah, 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 and 1. Using the information above, calculate the percent abundance of each isotope. Okay, so given that there are only 2 common isotopes, the percentage for each of them, percentage for both of them should add up to 100%. So let's say percentage abundance. So let's say I set percentage abundance of one of the isotope as X, then percentage abundance for the other isotope should be 100% minus X, or just 1 minus x. Okay, and now do you remember how we calculated average atomic mass for any of the elements? So average atomic mass of the neon should be equal to its weighted mass for all of the isotopes. And what I mean by the weighted mass is by multiplying its molar mass to its relative abundance or percentage abundance, and then add them up. So it's going to be the X percentage multiplied by its molar mass 19.99 grams per mole, plus the percentage abundance for the other isotope, 1 minus X multiplied by 21.99 grams per mole. And then this is equal to the average atomic mass of neon, which is 20.18 grams per mole. So now I just need to solve this equation. There's a linear equation. 19.99x plus 21.99 minus 21.99x is equal to 20.18. So 21.99 minus 2x is equal to 20.18. Then 2x is equal to 21.99 minus 20.18. And then by using our calculator, that's equal to 1.81. So x is equal to 0.905. Okay, so in percentage, that's equal to 90.5%. And we can easily calculate the percentage abundance of the other isotope. 1 minus x is equal to 9.5%. So that's it. So now we just use a linear equation to calculate the percentage abundance for both of the isotopes of the neon. And now let's take a look at number 2. Calculate the number of the neon-22 atoms in a 12.55 grams sample of naturally occurring neon. Okay, the number of the neon-22, well, it's about the number of, it's not the mole, it's a number of the particles. So I know for sure that how we calculate the number of the particles is by using the formula of N is equal to N times Na. The capital letter N represents the number of the particles. Number of the particles is equal to the moles multiplied by the Avogadro's number, 6.022 times 10 to the 23. To calculate the number of the neon-22 atoms, I need to calculate its moles first. So we're given 12.55 grams, which is mass. So for mass, we need to calculate the number of the moles and then calculate the number of the particles. So again, the conversion between the mass and the moles. Again, that's mass is equal to number of moles times the molar mass. So N is equal to mass divided by molar mass. That is equal to 12.55 grams divided by the molar mass of the neon that we just calculated in part A. Sorry, not part A, it's given. That's 20.18 grams per mole. Then we have 0.624 moles of the neon. Okay, but again, this is not neon-22, this is just the neon. And then we're going to calculate the number of the moles of the neon. Neon-22, okay. So neon-22 occupies 9.5% of the whole sample of the neon, which means the number of the neon-22 should also be only 9.5% of the number of moles of the whole neon sample. So it's 9.5% times 0.624 moles. And that is 0.0593 moles. And next, finally, we can do the conversion between the number of the moles and the number of the particles. So we know that the number of the atoms of the neon-22 is equal to mole multiplied by its mole multiplied by the Avogadro's number Na. So that's 0.0593 multiplied by 6.022 times 10 to the 23 neon 22 atoms per mole. And then by using a calculator, we get the answer of 3.57 times 10 to the 21 neon 22 atoms. So there are 3 steps. Again, there are 3 steps for part 2. So part 1 was pretty easy. There are 3 steps for part 2. The first step is to convert between the mass, convert from mass of the sample to the moles. And then the second step is you convert from the moles of the neon, the number of the both neon isotopes, to moles of the one of the neon isotope. And then the last step, the third step, is going from the moles of the neon 22 to the atoms of the neon 22 by multiplying by the Avogadro's number. Okay, so that's it. So now we're done with the mass, molar mass, and the moles, and number of the atoms, number of the particles. And next, I'm going to talk about how we categorize the pure substance. So there are different ways that we categorize pure substance. First off, we can categorize pure substance into 3 different categories depending on their phase or the states. So solid, liquid, gas, very simple, right? And actually, to be honest, we're going to go over these 3 states in unit 4. So you don't have to, unit 3 or unit 4, so you don't have to worry about it for now. Just remember that these 3 states only apply for the pure substance. When it comes to the mixture, such as the rubber or the glass, there can be more than 3 phases. And then how we identify or how we differentiate between these 3 states depends on how the atoms or the molecules are arranged relative to each other. So let's say for the solid, we call it solid because they have the fixed shape and then they have the fixed volume. So let's say this calculator, this is the plastic, or let's say this is the rubber. Yeah, this is the phone case for my iPhone. So both of them are considered, they are considered as solid. So they have the fixed shape. I cannot just stretch it or compress it. Well, and they also have the fixed volume. So their volume is not going to take the volume of a container, right? Like when I put my phone case in a bigger container, it doesn't mean that it's going to just expand and occupy the whole container. And it's because these particles, tiny particles such as atoms or molecules, they're arranged, they're tightly packed. So they're packed really tightly, and then they're very close to each other. So there's not so much space for them to expand or stretch. So they can only vibrate fixed at that position, fixed at a specific position. And then they cannot also go around each other. They're not free to move when it comes to solid. So that explains why the shape is fixed and the volume is also fixed. Then what about the liquid? Okay, when it comes to liquids, the particles are also close to each other. So, but they're only loosely attached. So when I say loosely attached, it means just like the beads. So think of the necklace. You have the per necklace, and then the beads are connected to each other. But still, they can just the beads are not. If the beads or the necklace, the per necklace does not have a fixed shape. Well, it can be arranged in a straight line. It can have the U shape. It can also have the S shaped. So they have the freedom to some extent. And when it comes to liquid, the particles can glide around each other. So it explains why liquid is fluid. Why, let's say when you pour it, so it doesn't have the shape, and it's going to take the shape of the container. If you put it in a beaker, it takes the shape of the beaker. If you put it in the flask, it takes the shape of the flask because of these because of the freedom they have to move around each other. When it comes to the gas, well, gas is the most free the phase when it comes to pure substance. So think of a balloon. Well, let's say you have a balloon. You can actually compress it to some extent. Well, you cannot compress it too much. Still, you can compress it a little bit. It's because when it comes to the gas, they do not have the fixed volume or the fixed shape. So when it comes to the gas, in between the particles, there is a lot of space or a lot of distance, and they are free to move. The gas particles are free to move around in this container. So that explains why no fixed shape and no fixed volume when it comes to the gas. Well, again, I will go over this part more in detail when it comes to I forgot, either unit 3 or 4, so we don't have to worry about it for now. And and then there are couples of ways to categorize the pure substance. To categorize the matter. So here is a really important flow chart that you need to remember when it comes to matter. So when it comes, what I call by the matter is just substance or stuff. So anything in the world can be called matter or the substance. And then we can categorize them into either pure substance or the mixture. So anything can be is either pure substance or the mixture. And pure substance is either elements or compounds. Well, here when it comes to elements, that has a different meaning than the elements in this periodic table. Because in this periodic table, element is just a specific type of an element, such as boron is a type of an atom, carbon is a type of atom. But here, when it comes to the matter, the elements means that it's a substance that consists of only one single type of the atoms. Okay, so what I mean by that is, for example, the iron is an element because iron, such as the iron, let's say, I don't know, the iron plate, iron earring, the iron jewelry, or whatever the matter that consists of iron is composed of the iron atoms only. Well, to be more specific, it should be the iron cations. So it consists of the iron only. So Fe by itself represents the iron. Okay, then what about the oxygen? The oxygen gas that we breathe in at every single moment for survival. So it's not just one single atom O. It's O2. The oxygen gas that we breathe in, it's O2, not just O. You cannot breathe in just so oxygen does not exist in nature just by itself. So O is extremely unstable. O2 is the stable form that can exist at room temperature on Earth in nature. So what you breathe in is O2. Well, even though there are two atoms, still these two atoms are of the same type, O2, oxygen. Well, what about ozone? So ozone is O3. Again, ozone is also a pure substance and it's the elements because each of the ozone molecules consists of one type of the atoms only, which is oxygen. So even though ozone and oxygen gas are two different matter, both of them are considered elements. What about hydrogen gas? Hydrogen gas, again, it's also H2, the nitrogen gas N2. All of these are considered elements. What are some other examples, such as the diamond, which consists of the pure carbon? It can be just written in the form of carbon, C, that's it. These are considered elements. Then what about compounds? So compounds are pure substance that consists of two or more different types of the atoms. So there are so many examples of the compounds, such as water, H2O. Well, hydrogen, hydrogen and oxygen, it's two different types of the atoms, right? So H2O is a compound. Table salt, sodium chloride Na, and Cl, sodium and chlorine, there are two different types of the atoms, so it's compounds. The ammonia, NH4, let's say ammonium, ammonia is NH3, and ammonium is NH4, 4 plus. Ammonium, NH4 plus, and ammonia is NH3. So both of them are considered the compounds. So most of the pure substance are actually compounds. Obviously, there are way, way, way more compounds than the elements. Well, let's say okay, and then next it's going to be the mixture. So how we define a mixture is actually very easy. So mixture just means when you combine or when you have multiple pure substance, then they're mixed together, they're just mixture. Well, it can be the elements and elements, or it can be the combination of compounds and compounds, or it can be the combination of elements and compounds. So let's say, for example, you have a cup of water, and then you're gonna add some table salt in it, and then you just put a little bit amount of table salt, and then you just mix it really well, so all the table salt is dissolved. Then this is a mixture. it has water, H2O in it. It also has the salt, sodium chloride in it. So that's considered a mixture. And because they're mixed evenly. So when I say evenly, it means when you have a cup of saline solution or salt water, then when you take a small sample from here and another small sample from here, they taste exactly the same, assuming that all of the table salt has been dissolved perfectly. So you're not gonna have different tastes here and here, right? So that's what we mean by it's mixed evenly and thoroughly. Then this is called homogeneous mixture. So homo means the same in Greek. So homogeneous mixture means it's same mixture or everything is mixed the same. So every part of this mixture is exactly the same. So what are some of the examples? So let's say you're gonna mix the water and the alcohol. So you can actually mix them thoroughly, and then this is going to be the homogeneous mixture because they're mixed. They can be mixed thoroughly. So such as salt water and then all of the alloys. Alloys means it's a mixture of different matters, the metals. So such as the iron and copper. So when you mix iron and copper, you're gonna like melt them at really high temperature, and then they're mixed thoroughly. Um, that's the homogeneous mixture. And then what else? Okay. And next is heterogeneous. Okay, next is a heterogeneous mixture. So contrary to the homogeneous, heterogeneous means two or more pure substances are mixed, but not evenly or not thoroughly. So a lot of the mixtures are heterogeneous. Well, such as the latte you drink. So latte has like a layer of cream at the top, right? You have the liquid at the bottom and you have a cream at the top. So these two parts are not mixed thoroughly, then it's heterogeneous mixture. Such as the pizza, you have a dough at the bottom and a layer of cheese, a layer of sauce, and then you have a lot of toppings on it. It's not like everything is mixed thoroughly, so it's heterogeneous. Or salad, you have the dressing at the top, and then you have the veggies at the bottom. So all of these are considered heterogeneous mixture. Or yeah, there are so many examples out there. So anyway, any of the matter, any substance in the world can be fall under all of any of these four categories. And then, okay, so that's it. So I just finished the macro perspective way to observe the matter in real world when it comes to chemistry. And now I'm going to talk about the micro perspective, which is the atomic structure. And this is also one of the most important part of the Unit 1 in chemistry. So I'm going to briefly go over the history of the atomic structure. So these days, we all know that all of these matters, it doesn't matter if it's pure substance or a mixture. It doesn't matter if it's elements, compounds, or whatever. Anyway, all of this, they are comprised of the tiny building blocks called atoms. But the idea of atom is actually pretty recent. So Dalton is the very first scientist ever in the history who proposed the idea of the atom. So he's the very first one who claimed that, oh, I think all the matter in the world is comprised of the tiny particles called atoms. And then he proposed that this atom is like a tiny sphere, a solid and divisible sphere of the matter. And then he proposed these ideas in 1803, which is about 200 years ago, right? So it's pretty recent. Well, so this is actually just a summary. He actually wrote like dozens of pages of the paper. We're not going to read over it. So actually the first part is correct. All matter is comprised of small particles. That part is correct, but some of his proposal was not correct. Well, the second one is he claimed that atoms are indivisible. Well, tell me, is this true or false? Based on the modern chemistry, based on what you know these days, atoms are indivisible. Anybody want to type the answer in the chat box? The atoms are indivisible. Correct or incorrect? Okay, so false. Yeah, perfect. So someone type in the chat box, it's false. So these days we know that atoms is comprised of the neutrons and the electrons. nucleus and the electrons. And nucleus also consists of the protons and neutrons. So atoms are indivisible. This is actually the false. And what about the third one? All atoms of a particular element have identical mass and properties. So this is considered correct, but only partially correct, because we just talked about the idea of the isotopes. So when it comes to the same isotope of an atom, then they have exactly identical mass and the properties. But if they have different, when it comes to the different isotopes, they have different mass. And then they might also have different chemical properties. Well, I just watched the Oppenheimer in August. Not sure if all of you guys have watched it. And then they're talking about the atomic bomb and the hydrogen bomb, right? Okay, they were talking about the isotopes in the movie. So when it comes to a hydrogen bomb, you cannot just make it using a regular hydrogen. So regular hydrogen has one proton and then no neutrons, right? You cannot make a bomb using this. You need to use the deuterium, which means it has a neutron in it. So it has one proton and then one neutron. That's what we call by the deuterium. That's the isotope of a hydrogen. So one can be the bomb, the other cannot, which means they have different chemical properties. So the third one is actually also not correct. So it's only partially correct. This is correct when it comes to the same type of isotope. Okay, and about 100 years later, because remember that Dalton proposed the idea of atom back in the 1807 or 1803. Yeah, and approximately 100 years later, another scientist, J.J. Thomson. Well, this name is also mentioned in the movie Oppenheimer. So J.J. Thomson is the scientist who discovered electrons. So before that, we didn't even know about the existence of the electrons. We didn't know about the charges. Okay, so once he discovered that there's something called negative charge and it's called electrons. A few years later, he proposed a new idea. He proposed a new model called plum pudding model, or we also call it chocolate chip cookie model, because he believed that atom is just like a chocolate chip cookie, and then the dough, the whole thing carries a positive charge, and then the chocolate chip, which are embedded randomly on this chocolate chip, carries a negative charge. The whole thing, the cookie, the dough carries positive charge, and then these tiny electrons carries negative charge, and then they are embedded thoroughly on this chocolate chip cookie. That's what he believed. Now, I mean, these days we know that this is incorrect. Okay, so who's the scientist who opposed this plum pudding model? Is the Rutherford. So Rutherford conducted a really famous experiment in the history of chemistry. This is one of the most important and then one of the most well-known experiment ever in the history of chemistry. It's called gold foil experiment. So he got a very thin gold foil, very thin layer of gold foil, very thin, like as thin as paper or even thinner than a paper. And then he placed it at the center. And then on one side, he has a radioactive source, such as the radioactive uranium or something similar to it. Okay, so the radioactive means that it's gonna emit this energy or the light, right? And then he just poked a tiny hole on this box to make sure that there is only one ray of the light, a straight ray of the light, and then it's shot straight into the gold foil. Okay, so what he proposed or what he expected is, okay, so based on the J.J. Thomson's plum pudding model, because the electrons are thoroughly arranged inside the atom, so it should just go through all of these radioactive rays should just go through it. They should just pass the atoms like directly. So he expects to see that all of the rays fall on the other side of the radioactive source. Okay, but the result turns out that actually he spotted multiple other spots on this screen. So this is a screen or a detector that can capture all of this radioactive light. Okay, and then he observed that most of the lights fall on the opposite side, okay, which is true, but some of them deviate from this straight line, and then some of them deviate even more by a larger degree like this, and some of them even reflect backward like this, even by a much greater angle. So he came up with this new model. Okay, so now he proposed that, well, I think J.J. Thomson's proposal for the atomic structure is not correct. So most of the radioactive light passed through the atom. This means that the atom, most of the space of the atom is occupied by nothing. It's just empty. So that's why the light can just pass it. But there must be a very dense nucleus at the center, and then which blocks the light from going through. So that explains why some of the lights reflect backward, while some of the other lights deviate by a smaller angle. So this is the result of the Rutherford-Goldfuss experiment. Okay, and then based on this, around in 1900, the Bohr is also another scientist that's mentioned in Oppenheimer. So Bohr came up with a new model. We call it Bohr model, and this is really famous, and everyone has seen this in your chemistry textbook, right? So he proposed a model called Bohr model, and then in this Bohr model, he claims that the electrons travel around the nucleus, but not in one single orbital. So electrons move around the nucleus, but when people live in a building, they do not live like randomly anywhere, right? In a building, they're either in the first floor or the second floor or the third floor. Like it's impossible for someone to reside in like 1.5 floors or like in between 2 and 3 floors, right? It can only be the whole number of floors. So that's the same when it comes to a Bohr model. The electrons can reside only in like certain levels or certain orbits, and we call this orbits, or we call it energy level. And then how we count it is from the innermost, we call it n equals 1. And then the next innermost is n equals 2. And then the next is n equals 3. And then there are infinitely many energy levels. And then when you go away from the nucleus to the outer side, we call that the energy level increases. Okay, so higher energy level means that obviously the electrons carry a bigger energy, and then the smaller energy level or the lower energy level means that the electrons are more stable because they carry a lower amount of energy. So first off, Bohr proposed that electrons can only reside on certain energy level, and then he also proposed that if electrons want to move between the energy levels or move between the orbits, that the electrons must be emitting the energy or absorbing the energy. So emitting means releasing the energy. So obviously, releasing energy occurs when the electrons jump from a higher energy level back to the lower energy level. And then electrons absorb energy when they're trying to jump upward from release energy is by the light. So when they release energy, it's by the light. So you observe. That's why you observe a certain colors. When the excited atoms release the energy, or they're going to absorb a certain the light of the certain frequency. And how he proves his model is by conducting this really important, really famous experiment, and then his result can be shown as the hydrogen spectrum. Well, again, I'm pretty sure all of you guys have read this, or your teacher have talked about this in classroom, the hydrogen spectrum. So the hydrogen spectrum, how it looks is everything is just all black, and then there are certain bars there, and in certain positions you observe the bars, and then these bars they're marked with different colors, and it's because the lights of different colors, they carry different amount of energy, and then this experiment proves that when in a hydrogen, when electrons jump back and forth in between the energy levels, they observe or they emit only a certain levels of the energy. They're not going to take the whole amount of energy from here all the way to the other way. So they're going to only observe a certain amount of energy, such as the energy at like 400 nanometers of the wavelength, or 700 nanometers of the wavelength. And here you do not have to memorize like the corresponding amount of energy for the electrons. You just need to have a basic idea of what it means by the Moore model, and you need to know that, oh, the electrons absorb energy when it jumps up, and then it releases energy when it jumps down. Okay, so this is a brief summary of the atomic structure and its history. Well, the Bohr model is the one that's closest to the modern the atom structure. But these days, we came up with a more advanced atomic structure, which is called by electron cloud. So this is what we believe today. So electron cloud means that electrons, in Bohr model, electrons move around the nucleus and they do a circular motion. But instead, these days we believe that they move around the nucleus, not in a circle. They can have like a lot of weird shapes, such as the donut shape, such as these the ribbon shaped or the circular shaped. It depends on which orbitals they have, which sublevels they have, S, P, D, F. And on top of that, we also these days we also believe that electrons do not move along a very specific path. They don't. So they can move like this. They can also move like this. Nobody knows that. We can only know that they will be in this area like 90% of the times. So that's why we call it electron cloud. And then we spot out all of the probability, the possible position of the electrons. And then about 90%, the position of where electrons might be for the 90% is what we call by the electron cloud. Okay, and next is the orbital fillings. This is also really important because you need to understand what it means, and so that you can learn the electron configuration. Okay, so we just talked about the Bohr model and different energy levels, right? So think of it as a bigger level, each of the floor when it comes to a building. And then inside each of, on each of the floor, there are also sub-levels or sub-floors. And that's what we call by the subshells. So this is n equals 1. Let's say this is a nucleus, and this is n equals 1, this is n equals 2, and this is n equals 3. Okay, when it comes to n equals 1, there is only one sublevel, which is 1s. When it comes to n equals 2, there are two sublevels. One is 1s, the other one is, 2s. The lower one is 2s, and then the higher one is 2p. Okay, so sublevel means that even in one level, they can be differentiated into multiple levels. So when it comes to the energy level, 1s is the lowest, and then it's 2s, and then it's 2p. Okay, then how we differentiate between 2s and 2p is based on the shape. So the electrons move around the nucleus in different subshells based on the shape of the orbitals. So let's say for the s, it always have this spherical shape, sphere shape. And when it comes to the p, the p orbitals, they always have this dumbbell shape or the ribbon shape. And then when it comes to d, it can have this like a donut, double donut shape, or it can have like different shape depending on which subshell or which orbital it is. And then so S, P, D, F. So these four are considered subshells. So we have the energy level, N, and then we also have energy level, and then we also have subshell. So energy level is also called by the shell. And then inside each of the shell, there are subcategories or sublevels called subshells. And then inside each of the subshell, we also have orbitals. So what it means by orbitals is, okay, so let's say for P, there are three orbitals, 2px, 2py, and 2pz. What I mean by that is once an electron is in, let's say 2px, then this electron can only move inside a 2px. It cannot go from 2px to 2py. Okay, actually it can occur, but there must be some kind of stimulus. It needs to like absorb like some amount of energy to switch between the orbitals. Otherwise, it would just move in inside a 2px. It's not going to switch between the orbitals. And remember that each of these orbitals are on the same energy level. So it doesn't matter if you put the electrons in 2py or 2pz or 2px. The order doesn't matter. You just know that 2p is at a higher energy level than the 2s. Okay, so that's it. And then now let's talk about orbital fillings. You need to know the orders of the orbital fillings to properly to properly do the electron configuration or write the electron configuration. So what it means by orbital fillings is, okay, we know that an atom consists of the proton, neutrons, and electrons. Well, and there are certain ways or specific ways for us to fill the orbitals using the electrons. I mean, we know that the protons are just protons and neutrons, they're just clustered together and then they reside at the center, right? And then we know that they're like levels or the shells. So the electrons is always going to fill the shells from the lowest energy level to the higher energy level, like gradually one by one. But what's interesting is they do not follow the order of 1s2, 2s2, 2p, 3s2, 3p, 3d. Well, that would be ideal situation, but actually they don't follow this order. So you will always have to write this diagonal rule. So you just write them out, 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and then it goes on. And then you start from the right top corner to the left bottom corner. You just cross it using this diagonal. Okay, and then it's going to follow this order. And also for the SPDF, remember that for n equals 1, there is only one orbital s. For n equals 2, there are two orbitals s and p. For n equals 3, there are three orbitals s, p, d. Starting from 4, 5, 6, 7, and all the way up there, they have four orbitals, s, p, d, f, four subshells. Okay, so it's because electrons always occupy a lower energy orbital first before occupying a higher energy orbital. So it's kind of tricky, but let's say 3p. After 3p, the next higher energy sublevel is 4s rather than 3d. So that's why you fill the 4s first and then 3d. Okay, and then next, here are three principles that you need to follow to properly do the orbital fillings or properly do the electron, to properly write out the electron configuration of any of the atom or the ion. So you don't have to memorize these names, but you need to know these principles. The first one is called alpha principle, and it states that electrons fill the subshells of the lowest available energy, and then it fills the subshell of the higher energy, which means it's impossible to fill the 2p first and then 2s. That's not possible. You need to fill all of the 2s first, and then you can fill the 2p. Okay, it's impossible to fill the 3s and then go back to the 2s. No, you need to fill 1s first. After it's filled, you fill the 2s. After it's filled, you fill the 2p. After all of these things are filled, you fill the 3s, and then it goes on. Okay, again, remember that when it comes to 2p, there are three orbitals, but this electron, this single electron can be in 2px. You can also put it in 2py. You can also put it in 2pz. That doesn't matter because 2px, 2py, 2pz, these three orbitals, they're all on the same energy sublevels. So as for these three, the order doesn't matter. But up and down, when you go switch between 2s and 2p, the order does matter. And then the next is Pauli exclusion principle, which states that no two electrons can have the same electronic quantum numbers. Well, so electronic quantum numbers means it's either +2 or negative, or +1/2 or -1/2. So think of it as the way it moves around the orbital. So let's say in one orbital, one of the electron moves this way and then the other one moves the other way. Then they are assigned two different numbers. So this is not how it actually works because they do not just move in one direction, but think of it as just two separate routes of the electrons in one single orbital. So how we represent it on the electron configuration graph is by the arrow up and arrow down. So in one single box for each of the orbital, there must be one pair of electrons. One is up and the other one is down. So it's impossible to have two up or two down. Well, but it's possible to have one down and one up. The order doesn't matter. One up and one down, or one down and one up. That's the same. Both can work. And then the last one is Hund's rule, which states that every orbital in a shell is singly occupied with one electron before any one orbital is doubly occupied. So what does that mean exactly? Okay, so what it means is, let's say you have two more electrons here. Okay, then how you put it in this 2p sublevel is not like, okay, one and then the other one, okay, a pair and then third here. No. or one here, the other one here, the third one here. No, it's not like that. You have to occupy every single room or every single orbit first. So 1, 2, 3. And then if you have extra electron, then you can put it here, or you can put it here, or you can put it here. But first, you need to fill in every single room or every single orbit first. Okay, so why don't we try to do some practice on how we properly write the electron configuration. So let's say, for example, for the silicon, okay, so silicon has 14. Silicon has an atomic number of 14. This means that it has 14 protons. It also means that it has 14 electrons. Okay, so now we're given that 1, 2, 3, 4, 5. Okay, so where do I put the 6th electron? It must be here because I need to occupy each of the orbit before pairing them. So it should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 electrons. Now we have 4 more. Okay, 10, 11, 12, and then 13, 14. Okay, then what about this? Can I put this? Yeah, that also works. Okay, then what about this? Does that work? No, this one doesn't work. So if you want to fill in single electrons in each of the orbit, they have to be either up, 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 or down, down, down. You cannot mix up and down until they're paired. So again, up and up, this works. Or up and up, this also works. Okay, and up, this also works. Or you can even do down, down, or down, down, or down, down. Any of these work, but just remember that do not try to mix them and one up, one down. No. Okay, then what about this one? Let's say the magnesium. Okay, magnesium has a atomic number of 12. Magnesium has a atomic number of 12. That means that it has a proton number of 12 and an electron number of 12. Again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's it for magnesium. Okay, so that's it. That's the orbital fillings and electron configuration. And then now that's going to be the periodic trends. We're almost done with a unit 1. Okay. So when it comes to periodic trends, again, I mentioned that there are 4 parts, 4 quantities that you need to know or you need to memorize. One is atomic size. The other one is the ionization energy, and then the third one is electronegativity. The last one is electron affinity. The third and then the fourth are especially confusing because their names are even like similar. Electron affinity, electron affinity, and electronegativity, but they are 2 different concepts. Okay, so I'm gonna start from the atomic size or the atomic radius. They're basically the same. And also, this is the part that you get tested the most in AP chemistry. Okay, so when you go from left to the right on a periodic table, okay, again, when we talk about the periodic trend, we're just assuming that we're not including this part. We're not including the transition metals. When it comes to periodic trend, usually we're talking about the left side, the left 2 columns, and then the right 6 columns. Usually we do not consider the transition metal because they do not quite fit in this trend. Okay, when you go from left to the right along the period, so we call the row period, and then we call the column the group. So when you go from left to the right across the period, the atomic size decreases, and this is because on one single row or on one single period, they have the same number of they have approximately the same number of the they're on the same energy level. Yeah, the energy, the shell or the energy level are the same for all of the atoms on one single row or in the same period. But when you go from left to the right, the number of the nucleus, the number of the proton increases. This means that the effective nuclear charge increases. So this is something that you need to memorize when it comes to the FRQ. the effective nuclear charge means it's a attraction force of the nucleus toward the electrons, toward the valence electrons. We know that valence electrons means the outermost electrons, the electrons in the outermost shell. So because of the increasing number of the protons, there is a stronger pull on the electrons. So the whole thing just shrink in size. So it explains why the atomic radius decreased from left to right. From top to the bottom, it's much easier to understand. From top to the bottom, the energy shell just increased. So think of just think of, let's say, the Romanian lettuce. When you have one more shell, then the size just gets bigger. When you have one more shell, the size gets bigger. Okay, and then what about the okay, so that's it for the atomic radius. Okay, and then the next is the comparison of the size between the atoms and the ions. Okay, so when you're comparing the size of an atom to its cation, usually the cation has a much smaller size, while the anion has a much bigger size. It's because when you convert from an atom to its cation, actually the atom loses an electron. So it loses an electron, and then its energy shell actually decreased by one. So let's say lithium. So the lithium has two energy shells. Lithium nucleus, and then it has one shell and then two shell, n equals 2. But once it's converted to lithium plus, it's going to lose the electron on the outermost shell. So now it actually have only one shell, n equals 1. There are two electrons here. So because of this decrease in the shell or decrease in the energy level, its size decreases like suddenly. It decreases by a lot. And when you compare the atom to the size of its anion, then it's the other way around. Because usually you're adding the electrons on the electron when you convert it from atom to the anion, which means it has one more shell. So let's say the chlorine and then the chloride ion. So chlorine has 3 shells. So the nucleus, n equals 1, n equals 2, and n equals 3. So originally chlorine only had like 7 electrons here. And then by adding one more electrons, because of the repulsion between the electrons, because of the repulsion between the negatively charged electrons, electrons are gonna push against each other more. So it just naturally expand in size. So that explains why the anions are always bigger or larger than the atom, while the cations are smaller than the atom. Okay, so that's it. And then the next is the ionization energy. So that's also a pretty important concept. So ionization energy is the amount of energy required to remove a valence electron from any of the atom or an ion. Remember, it's always removing it, and it always requires energy. So think of it. So let's say you have a Romanian lettuce again, and then you're trying to remove the leaf. You're trying to remove the outermost leaf from it. Then you will have to actually put in your energy to remove that, to pick it up. So that's the scene. When you're trying to remove an electron from an atom or ion, it requires the energy, which means it needs to absorb an energy. And then we call that amount of energy as ionization energy. So think of it this way. So when the valence electrons are more tightly bound to this atom, the ionization energy is bigger. It requires more energy because it's more difficult to remove that. If it's really easy to just remove it, then it has a very small ionization energy. Okay, and when you go from left to the right, remember that the atom decreases in size. And what does that mean? Decreasing in size was due to a higher effective nuclear charge, which means a higher attraction force applied by the nucleus on the electron. So it gets more difficult to remove that. So also imagine that I am holding something loosely versus I'm holding something tightly. Then when you're holding something tightly, it's more difficult to get that away from you, to remove that away from you. So it requires a greater energy. So ionization energy increases from left to the right across the period. When you go from top to the bottom, because of increase in size, the valence electrons are further away from the nucleus, which means the valence electrons are more loosely attached to the nucleus. So it's pretty easy to just remove that electron from this atom. So that's why ionization energy decreases from top to the bottom. Okay, so That's it for ionization energy. But okay, so there is a general rule for general trend, which is from left to the right, ionization energy increase, from top to the bottom, ionization energy decrease. But there are two exceptions when it comes to ionization energy, and this is something that can be so this is something that can be tested in AP chemistry test. So when you go from the second row to the third oh yeah, so when you go from yeah, so wait, when you go from the fifth to when you go from fifth to the sixth, or when you go from second to the third, the ionization energy actually decreases rather than increase. So we know that from left to the right, it should increase, right? That's a general trend. But when you go from the second column to the third column, ionization energy decreases. When you go from the fifth to the sixth column, ionization energy also decreases. Okay, and this is because of the fully filled, the fully occupied orbital, and then half filled orbital. So okay, and let's take a look at this orbital filling graph. And now let's try to compare the phosphorus and sulfur. So phosphorus is in the fifth column, and then the sulfur is in the sixth column, right? So for the phosphorus, it has 1, 2, 3, 4, 5 valence electrons. So 3s2 and 3p3. So this is the valence electron, 5 valence electrons of the phosphorus. And now you notice that in 3p orbital, this is half filled. So p orbitals have six spots for the electrons in total, and then now exactly half of them are filled. Okay, so this is considered pretty stable. I mean, not as stable as fully filled, but still pretty stable. On the other hand, the sulfur, which has one more valence electron, or six valence electrons. It has 1, 2, 3, 4, 5, 6. Okay, so it has one extra electrons in one of the 3p orbital. So compared to the phosphorus, this is less stable. Okay, and the less stable always means the higher energy. Stable always means the lower energy. Stable is always lower energy, and then unstable, or I'm just gonna put unstable. Unstable always means that it is a higher energy. So when you're trying to add one electron, you are always switching from a stable to the unstable state. Okay, so what does it mean by unstable? Unstable means to knock off this extra electron is going to be pretty easy. It's not going to require much of the energy. Why? Because it's already unstable state. So you just give it a little bit amount of push or pull, and then this electron will just be knocked off. Because everything in the world, either in chemistry or physics, they always prefer the more stable state. They're eager to go from unstable to stable. So it's pretty easy to remove this one. So that's why the ionization energy decreases when you switch from the fifth to the sixth column. Okay, and that's also similar when it comes to the switch between the second and then the third. Yeah, so this is the switch between the second and then the third. So because of the fully filled orbitals, so the second, the element or the atoms in the second column is considered very, very, very stable. So such as lithium, such as beryllium. So beryllium has 2 valence electrons, which means it's gonna all occupy it. The 2s orbitals are fully filled. Okay, so even though 2p is not fully filled, but one of the sublevels are fully filled. So this is considered really, really, really stable. On the other hand, the boron, which has 3 valence electrons, has 1, 2, 3. Okay, so there is one single electron in 2p orbitals, right? So again, this is one extra electron, which makes it less stable or unstable, which means it is at a higher energy level. So it's pretty easy to just knock off this electron. So that explains why it does not require much energy, or it requires a less amount of energy to remove this than removing this. So this is how the ionization energy trend looks for all of the atoms in one period. So in general, it's an increasing trend, but when you go from second to the third column, it decreases, and then when you go from fifth to the sixth column, it also decreases. But in general, it's increasing. So that's the ionization energy trend. And then the next two are electronegativity and electron affinity. Okay, so first off, let's talk about electron affinity. So electron affinity is the opposite of ionization energy. Remember that ionization energy occurs when you're trying to remove an electron. Then this time you're trying to add an electron on an atom. So when this electron acquires or captures an extra electron, it's going to release a certain amount of energy, and then that energy is called electron affinity. So that's the amount of energy released when an electron is added to a neutral atom. Okay, so electron affinity also measures the ability to accept an electron. Okay, so electron affinity also increases across a period. Okay, think of it. When you go from left to right, it's getting more and more positive, right? So let's try to compare let's try to compare, let's try to compare the lithium and the fluorine. Okay, both of them are in the second row or the second period. So the fluorine has more electrons compared to the lithium. So when fluorine captures one electron, then it will immediately become the most stable, the octet state, right? On the other hand, when it comes to lithium, even if you add one atom, it's not gonna make too much difference, because out of the 8 valence electron spots, now it has only 2. So one versus 2, not so much difference. Still far away from a full-filled octet state. So that's why when fluorine acquires one electron, it becomes like very stable compared to its original state. Like fluorine is this much unstable, but fluorine minus is like extremely stable. So the difference between these two states are very big. On the other hand, when it comes to lithium, well, lithium is this much unstable. Lithium plus is slightly more stable. The gap between these two states are not so much difference. The bigger the gap, in between them, in between these two states, the bigger the electron affinity. And you go from up to the bottom, electron affinity decreases when you go down a group. And it's because when the electron shell increases, or when the energy level increases, again, adding one electron on top of it does not bring much of an effect. Well, usually when you add an electron, it becomes more stable, but because the valence shell is so far away from the nucleus, so it doesn't matter much. It doesn't matter much that it has one valence electron or 2 valence electron. It doesn't affect the nucleus as much. And then the last one is electronegativity. Okay, so again, electronegativity is usually confused with electron affinity. So even though they pronounce similar, but there are 2 completely different concepts. Again, ionization energy is the energy, so it's measured in joules, and electron affinity is also the energy, the amount of energy released. That's also measured in joules. On the other hand, electronegativity is the tendency or the extent. So it's represented in terms of some number that we arbitrarily created on the scale, but there's no unit, because it just represents a level. So let's say, oh, the pain level, like let's rate the pain level from 0 to 10. Well, that's just the number that we arbitrarily, it's a scale that we arbitrarily created, right? There's no such thing as like 5 pain level or 4 pain level, just descriptive. So that's the same for electronegativity. And then it measures the tendency or extent of an atom to attract the shared electrons. Again, so this is really important. The key point here is the shared electron. So electronegativity is extremely useful when it comes to the bond, the atomic bond, such as ionic bond, like the molecular bond, the covalent bond, ionic bond, and etc. So it measures how strongly an atom can attract the electrons when it combines with another atom. So it measures how greedy an atom is. So let's say I'm going to share electron with another and let's say I am an atom, I'm going to share electrons with another atom. Well, if I'm very greedy, I'm very powerful and strong, then I'm going to share. So even though we're sharing, I'm going to grab the electrons and pull it toward myself. That a lot of times, most of the times, the electrons are on my side rather than on the other person's side. That it means I have a very high electronegativity, while the other atom has a very small electronegativity. It's not powerful as me to grab these shared electrons. Um, so electronegativity, well, I don't know why I put electron affinity, but it should be electronegativity here. Electronegativity also increased from left to right because of the stronger the stronger effective nuclear charge, and it decreases from top to the bottom because of the increasing shell. Again, the valence shells are further away from the nucleus, so it experiences less of this pull or attraction from the nucleus. So that's it. So that's it for the unit one. Um, and I well, let's see. I might have some time to go over some of the progress check. Okay, so I don't think I have time to go over everything, but I can go over a few of the questions here. So let's see this one: 1s2, 2s2, 2p6, 3s2, 3p6. How many unpaired electrons are in the atom represented by the electron configuration above? Well, you don't even have to know which atom this is. It's just asking for the unpaired electrons. Again, remember that unpaired electron means that in each of the orbit, okay, this is unpaired, this is paired, right? So this is unpaired, this one is paired, this one is paired, this one is, these two are unpaired. Okay, so okay, now let's take a look at this electron configuration. I mean, 1s2, okay, because there are two, obviously it's paired. 2s2, again, it's paired. 2p6, it's fully filled, of course, so that's going to be three paired, three pair of the paired electrons, and then 3s2, 3p6, all of them are paired. So no, there are no unpaired electrons. So A is the right answer. Also, will you be planning to do AP Physics C? If there are a lot of people requesting it, I will, but up until now, I didn't see anybody requesting it, the Physics C. And for the AP Physics C, because content-wise or the concept-wise, it's actually 90% of it is the same as the AP Physics 1. It's just the way you solve the problem. Especially the FRQ is the FRQ question is of a very different style. So I might go over the FRQ of the AP Physics C if a lot of people request, but I don't think I'm gonna make a separate contents for that. But I will do it for AP Physics 1. No, sorry, I didn't do the bio. Yeah. I didn't take AP bio. I took the IB program, and then I self-studied for AP. So I know everything about the chem and physics, but not the bio part. And that's the same for the physics too. If there are a lot of people requesting it, I will do it. But for now, I only see the physics 1. Oh, physics C. Okay. Okay, and then okay, so rubidium Rb reacts with oxygen in a mole ratio of 2 to 1. Okay, forming the ionic compounds of rubidium oxide. Okay, which of the following elements will react with oxygen in a mole ratio of 2 to 1? Okay, so this is actually about this is asking about the periodic trend. So so rubidium is a type of metal, right? And then it reacts with oxygen at the ratio of 2 to 1. And it means that all of the atoms or all of the elements in the same group will react with oxygen at the same ratio. So it's just asking for which of these 4 elements is in the same group as rubidium. So Rb is right here, it's in group 1, right? Okay, so which one is it? Okay, not okay. It's the cesium, obviously. Okay, and next, okay, probably this one. Which of the following represents the electron configuration of an oxygen atom in the ground state? Okay, of an oxygen. So first off, I need to determine how many electrons oxygen has. So oxygen has a proton number of 8, which means it also has an 8 electrons because it's an atom, not ions. So okay, so it must be if I write out the electron configuration, there should be 1s2, 2s2, 2p, okay, 8 electrons, 2p4. So I can cross out A and B because A has only 2p2 and B has only 2p3. So obviously A and B are not the correct one. And then out of C and D, okay, I need to choose the one that follows the correct rules out of those three principles. Okay, and as for the D, I know that's not correct immediately because according to the Hund's rule, you need to fill in every single orbital by single electron first, and then you fill in the same orbital to have the paired electrons. So you should fill in these three orbitals first, and then you fill in the extra electron in one of these three orbits to form one paired electrons and then two unpaired electrons. So the answer should be C. Okay. So it's 8:51 and then I have a class later, so I need to stop here. So thank you guys for coming. And then it will be I really appreciate it if you put any of the feedback in the comment section. Any advice or any topics that you want me to go over. And also I want to know like what topics you're learning at school right now. Because usually it should be unit 1, but probably some of you guys are learning something else. So it will be really helpful for me to get prepared if you let me know like what topics we're learning at school right now. So that's it. So I'm gonna end the live stream and I will see you guys on Wednesday.